I'm Ying. I'm a player engineer at YouTube, and I'm here to talk about TVs. Here is my agenda today. Pretty straightforward. So let's go ahead. So why TVs? Well, if you listen to the internet, my generation was supposed to kill the TVs. And sadly, I'm here to report we failed. YouTube now has TV as its fastest growing device platform. And I think this trend holds across the industry. As you can see, there's a number going up and to the right. And we think this trend will continue for a few more years. So TVs are important. But another thing, if you listen to the voice of the internet, is that TVs don't always work. Some of them are our own bugs, unfortunately. But very often, it is bugs with the TV themselves. And that's what I'll be talking about. So before I get too deep into the rabbit hole, let me first explain what TV is. Just to be clear, the TV here is the device platform and not live TV. Just so happens YouTube runs on both space right now. So we support everything, going from all the game consoles, the major TV dongles, some oddballs like smart displays, as well as actual TVs. Basically, if you have a thing running YouTube, it's not a tablet, not a phone, and not a computer. It's a TV. As a result of this, we have more unique model numbers of TVs on YouTube than there are Android phones, which is already infamous for its fragmentation problems. So what are we running on these TVs? JavaScript. Turns out the YouTube app on TV is basically a mostly standard compliant website. And let me go through the stack here from bottom to top. On the bottom, we have all the chip vendors making chipsets for TVs. I think MediaTek is the largest one, and AMD makes the chip for PlayStation and Xbox. The TV manufacturers would then layer their own OSs on top of the chipset. There's Android TV and all its forks. There's Tizen from Samsung, LG's WebOS, and so on. Above that is Cobalt, our own custom browser. Cobalt exposes an porting layer called Starboard, where OS have to implement a bunch of APIs to support in order to run the browser. It has some basic system functions like threads, network sockets, storage, but there's also a bunch of media-specific APIs, because if you work with the TV chipset, there's a lot of firmware-level media operation. And Cobalt itself is just a stripped-down version of the browser. It supports a subset of web standard, the part that YouTube uses. And that's how we can run it on a bunch of low-end power devices where Chromium would never run without 8 gigs of RAM. On top of the browser, there's a player, and Google pays me to write JavaScript in there for a living. So the architecture has some implications. Because we're working with media source extension, the player is mostly blind to the actual media stack underneath. But surprisingly, despite us running our own browser, the browser is also blind to those things. Because, like I said earlier, it mostly acts as a proxy to the firmware level media operations. So everything is offloaded into a chipset. On mobile, if you want to, you can get your audio clock, get your individual frames, and do your own frame releasing logic. But in our case, we get a bunch of binary blob from the internet, throw it into a video element, and just pray for image showing up. So once we turn the media into the TV, we basically lose control over it. And if you pay attention to TV marketing recently, they are launching a bunch of AI video enhancement, where we do, well, not we, they do upscaling, auto HDR, motion smoothing, voice processing, and all that. None of these are exposed to us in the application layer, but all of them does partake in the media pipeline and affects the playback quality. So with that out of the way, what can go wrong in this thing? Here's a few examples. So first one, TV is mostly run on hardware decoders because they're too slow for software. And in the application layer, in the player, we normally communicate video spec by bitrate. So we go like, hey, TV, we have a VP9, 1080p, 30 FPS, 2 meg per second stream. Can you play it? And TV says, yes, no. Unfortunately, bitrate is not the most ideal way to test capability. If you think about it, by can you decode it, what we really mean is, hey, TV, can you decode every single frame of this video within a 33 millisecond time frame, at least for 30 FPS video, that is. And if it fails, then you have to drop the frame, drop a bunch more frames, and wait until the decoder can catch up, which causes stuttering, like the simulation down here. This processing is often bound by keyframes in a video, which tend to be the largest frame, and because they are the largest, they are the slowest to process. So if a decoder can decode all the keyframes, then it can most likely handle the rest of the video just fine, of course, assuming the codec is supported. But if you look at the plot above, where we have two videos at similar bitrate, the size of the keyframe is not perfectly correlated with bitrate, because that is dependent on what content is being encoded and how much motion is there, and so on and so forth. So we often have a case where we have two different videos encoded with the same profile. We give it to a cheap TV, and TV plays one fine and just stutters on the second one. The bitrate cannot test for this. This generally happens with the lower end of the firmware chipsets, where they are really pushing the boundaries on how slow stuff can be. And also when we release new codecs, like AV1 HDR, before the hardware decoder can mature. And we have needed to implement a bunch of heuristics to try to work around those issues like this. Frame rate is another common concern. You know how this works. You have a video at 24 FPS, you have a TV at 30 Hertz. And the plot above shows you how those two are mapped together. Basically, you have to convert every 4 frame into 5 frame for display. This can be done in many ways, but the one rendered here is you repeat 1 frame twice. Now, if you have a smooth panning motion in your video, this would cause juddering, where you see little skips in the video. Some higher-end TV boxes have the feature called match frame rate, which basically does a HDMI handshake. So it disconnects HDMI, look at what's being decoded, and reconnect at a new frame rate. This works for a lot of platforms, but for us, it's a bit inconvenient because we have a lot of shorter content and also more diverse because it's user-generated. You can also minimize this by getting either a high refresh rate display or a variable refresh display, both of which are used a lot in gaming monitors, but are starting to enter into the TV market. So talking about HDMI, that is kind of crazy. So you have a TV, you have a TV dongle, and you have a receiver. The TV dongle decodes the video, the frame is displayed on the TV, and the audio is piped all the way to the receiver for playback. And all 3 things just connected by HDMI and nothing else. That's just kind of magical if you think about it. So it turns out that HDMI is much more than just a pipe for audio and video data. It is also a negotiation protocol. The spec is like 300 pages long, which I did not read after opening it. So once you plug in HDMI, the device will negotiate on what frame rate to support, what resolution, what color space, and the bit depth. There's also additional metadata like AV sync, where you have a receiver saying, hey, it takes me 100 milliseconds to process this audio. And the TV, once see that, it will delay everything by 100 milliseconds to match everything. If this sounds a bit too good to be true, it is. So we have seen TVs, HDMI as a protocol, it's OK for negotiation, but it's a very bad error propagation pipeline. So there's no way for a downstream device to know or bubble up anything that's going wrong. So I've seen that TVs would go into HDR mode and never go back. We have seen receivers that just fail to decode audio. It's total silence, but the TV just plays the video onward because it doesn't know. And the issue is so common that if you buy a high-end TV dongle or TV box, there's often a manual for overriding codec support, which would basically be saying that the receiver is lying. It actually doesn't support ESS-RAY or whatever, and let's disable manually. The only reason this exists is for you to override what is not working with the HDMI protocol. And I've seen that a lot of devices would misconfigure their HDMI handshake in one way or another. So that's just 3 short examples of how fuzzy things can get on a TV. And what's next? If you were paying attention earlier, you would have seen that a common theme among the 3 issues I mentioned was that they are invisible to us, to the player. And they all happen at the hardware level. So here's 2 things that we know we want to measure. dropped frame is important for detecting decoder issue. If you drop frame, you're stuttering or something else. It's already available from MSC. We can query for that. But the data MSC gave us in this case is bubbling up from the underlying hardware, and there's no validation for it. And as you may know, if there's no validation, it does not work. So we have seen cases where the TV is dropping frames like hell and numbers is 0. Unfortunate. We also want to measure AV sync. Conceptually simple, how far is the video and audio drifting apart. But in the player, we don't have access to an accurate clock. And we also cannot measure the audio pipeline from within the player. So what do we do? If you were in the talk in the morning session, pointing a camera at the TV is an especially good way to do stuff because it simulates your eye. So what we did was we have a team in YouTube for pattern engineering. They're very helpful for this kind of stuff. They would be encoding a frame unique identifier. In this case, it's basically a counter going from 0 to 255 and going back down in loops. So with this pattern piping into a detector, we can now plot the audio and the video signal for the same pattern because the audio is also encoding this information. And if the video goes from 10 to 12 in the counter and skip 11, then you know one frame has been dropped. So it's great for frame drop detection. And if the video is saying this is frame 10, the audio is saying this is frame 8, then you know you have an AV sync issue of 2 frames roughly. So the zoomed in portion on top where the star is, you can actually see that the green line skipped vertically by 2 steps. It's a bit hard, but you can see it. So after collecting all this data, we can run analysis on it. Here we have a single TV where we turn off motion estimation, motion composition, basically motion smoothing. On the left side, we turn it off. And on the right, we turn it on. I won't go into too much details on this one because of time constraint. But one thing I want to point out is if you look at the upper right plot for both sets, that one is the average AV sync between the audio and the video. On the left, we have 22, which is the video is ahead of audio by 22 milliseconds. That's decent. On the right hand, where we enable the motion estimation, it dropped down to minus 80 milliseconds. For reference, 40 milliseconds is where we would normally say that a user can somewhat see something's going funny, so it's on the boundary of noticeability. So this one would outright fail on our sort of validation if you do validate for this thing. So by turning on this feature, the TV is adding 100 milliseconds into the video processing pipeline underneath us, so it's all on the firmware level, and not doing any composition in the audio level or in the audio layer. And this is the kind of issue that we get lots of complaints for, but we cannot detect and cannot fix. So this is something that this vendor should really track down in this case. This project is very much still a work in progress, but we are hoping that similar measurements will help us guide future device certification when we work with our TV partners. So on the other side of the story, I hope this is a shared experience. TVs are painfully slow. You just would open the app, it gets stuck randomly, then crash. You would get any TV from the store, get the remote, press the menu button, wait for 2 seconds of nothing happening, and then the menu starts sliding in from the set in stop motion animation. It's almost like as if the TV manufacturers are picking their chip specifically for barely able to run the operating system. This makes no sense. So why are TVs so freaking slow? A common answer I got is that the margin on TV is razor thin, so the TV have to go as cheap as possible when they are picking parts, apart from the panel, which is what they sell. But the more you dig into this issue, the more you feel wrong about this. On the plot here, we have a 3 CPU benchmark from the internet. The center one is the 2024 Android TV dongle that's released this year. And on the bottom here, we have 2015 Nexus 6P selling at $500. And you can see that it's twice as fast as our Android dongle this year. So the performance that we're looking at today on a medium high top tier TV dongle already existed in mobile chipset back in a decade ago. Now, as time passes on, 5 years later, in year 2020, Samsung released this phone that's $180. That is less than half the price and also 50% faster. So by 4 years ago, this kind of performance has already penetrated into the lowest end of the mobile space. And fast forward today, which is not on plot here, there's a successor to the A12 called A15. That chip doubled performance again and kept the price at $180 before accounting for inflation and all that. So now we have a $180 phone that is 4 times as fast as our Android TV dongle from the same model year. If you think about it, you get a phone, you take the display out, take the battery out, take the speaker out, and all that. You're left with a TV dongle that is $100. So why is our thing not 4 times as fast as it is? So there's a hint in the most performant TV box you can buy on market today. Those are two. You can get an Apple TV released 2 years ago, or you can buy an NVIDIA Shield, which is 5 years old and still one of the fastest non-Apple devices. That's kind of surprising. 5 years. That's a long time for chipsets. So if you were to ask me how would I build a TV dongle, I would have told you what I said earlier, despite not knowing anything about hardware, so take that with a grain of salt. I would just take a mobile chipset, stick it into a plastic box, and put HDMI port on it. TV dongle. But that's not what happened. Turns out smart TV started a long time ago. On the right here, we have 2 early examples of smart TV from 2009 and 2008. For reference, that's roughly the same time as the first generation iPhone. So smart TVs couldn't have borrowed a chipset from mobile for use because mobile chipset was not a thing. It was so early in time. Instead, it inherited chipsets from a different set of consumer electronics, DVD players and set-top boxes. And they are architecturally different from what we have in a mobile chipset. So over the next decade, so between 2009 and I guess 2019, yeah. They co-evolved, and sometimes they would cross-pollinate if there's benefits, but most of them just evolved separately. And the mobile chipset very soon outpaced the TV chipset because of the skyrocketing demand in that field. However, the TV chipset did not get as much demand, did not improve as much, but also, most importantly, because they were architecturally different. They couldn't have borrowed a lot of the free performance gain from the mobile chipset without adding on additional cost. So the result of that was over the next few years, so past couple years, there were some routine updates in the video pipeline to support new codecs, a bit more processing for stuff like upscaling. But the rest of the chipset really got very little, didn't get much love. The TV vendor also did not really had a demand for faster chips because for them, the apps didn't mean much. The TV is a video playing device. The apps are there to get the videos play and not the other way around. Changing architecture is possible. Apple has always used their older iPhone chipsets in their TV. And NVIDIA basically borrowed the Nintendo Switch's chipset, which they made for their Shield, trying to make it to a gaming platform. The rest of manufacturers, though, did not see a reason to invest in these things. And we stuck with TVs that got neither faster nor cheaper over the years. So my coworker told me that a talk should end with a call for action, so this is mine. As engineers and people who work on applications for TVs, we are shipping an application and not a video playing square, the video element. There are times when we want to do slightly fancier stuff. Maybe you want software compositing, maybe you want complicated animation overlay, maybe you want to run custom video filters, maybe you want a software decoder, David's great. And maybe you want to even run web codecs, and none of them are possible today on the existing TV hardware we have. So the next time that you work on something, a feature that is classified as technically infeasible for TVs, my ask is that if your company or team has outreach or relationship with TV vendors or manufacturers or chip vendors, tell them that the other side of this ecosystem have to know about the demand for faster, better TVs so we can escape this stagnation. And that's my talk. Thank you.